way you don't get the Twitch stream. Alright, let's hide Godot, since I started playing around with Godot again for some reason. Okie dokie. Sorry, lots of clicking happening off screen. Okay, how are we all doing today? I finally started getting homework 3 graded, which is now eons past. The other sections is fully graded. Yours is half graded because I fell asleep last night while grading it. So you should be getting feedback on that and your group work fairly soon once I get through it all. I'm kind of intentionally being nitpicky on them to get some of the points across of the differences of functional and non-functional requirements. I don't think anybody's gotten a really bad grade yet, so I wouldn't worry too much, but my comments might seem hypercritical, but take them as constructive criticism at least. So hopefully it's not too bad. If you have any questions about them, feel free to let me know. Again, you're not graded yet, so I wouldn't worry too much about that. And I just realized that didn't resize all the way there. Sorry. That's better, at least a little bit. Zoom. There we go. Okay. So today we are going to leave the world of design patterns and anti-patterns, and I was glad to see actually some of you talking about the design patterns and anti-patterns in the Discord chat, because there are a lot of funny ones out there. Definitely worth looking at that Wikipedia page if you haven't yet. Oh, I'm supposed to be doing lecture today through Discord chat, right? I think that's the new strategy I read in the other Discord channel, what we're supposed to be doing. But today what we're going to be talking about is kind of bringing it up a level. So we've been doing the diagramming, right? We've been doing lots of UML. We've kind of flown into design patterns, which takes what you've learned in UML and kind of applies ideal strategies for creating your code and structuring your projects, and shows you the bad ways to do that too, right? So that's the anti-patterns. Now we're kind of going to look at it kind of a step above in a way. So we're going to look at what I love to call the acronym lecture. Basically, we're looking at object-oriented analysis, design, and programming. So that's OOA, OOD, OOP. You probably all have heard of OOP. That's pretty much what you've done in Java, right, in your intro to programming classes where you have object-oriented constructs. But there's two other aspects to this whole software design lifecycle as well. And I'm pretty sure I named it OO star in Blackboard. But basically we have, again, these little extra things tacked on here. So we have analysis and design. And if any of you are interested in the graduate path, I'm currently teaching 641, which is object-oriented analysis and design. Does anybody have a guess as to what the difference between these are? I guess the cheating ways, you could look at the next couple slides, but obviously programming, this is your implementation details, right? But analysis and design, this is something different. You can just drop it into the chat if you have a guess. And if not, I will drop my little blob dance in there again. Assuming OOD is about designing a program with the intention of using. Hey, that is a very good guess. Right, so we are kind of in the middle of the engineering process with design. So analysis would be your first step that we perform, where we start to figure out the project. Design would be iterating that, introducing new objects, and trying to get it to that OOP level. So that's actually a really good answer. I should have put these out of order so that it wasn't a logical guess. But yeah, that's pretty much it. So OOA, This is where we look at the actual domain of your application. So what I like to tell my grad students in this, you know, analysis and design class is that you have to, excuse me, let me do that really quickly. Um, we are taking ourselves out of the programming picture and we are becoming software project managers. You are at a level above programming. Everything you do in analysis and design, you could package up and give to any programmer, and in theory, they could go ahead and implement your project. So here you care about developing the models, kind of the high level models of your domain. And domain is going to be your environment, it's going to be your project, all the components that you can think of. Basically, we're modeling everything out. So take those UML models that you learned before, and now we're structuring a project around that. So with that, we might care about which objects we have to create. We're going to care about what operations they may have to perform. And we're kind of looking at this from a nebulous problem level, right? So if you need to make a phone application that schedules your classes, the problem is you need a scheduler. What objects do you need to support that? What operations have to be performed? Looking through your requirements, you have very, very detailed ideas of what that would be, right? Or if you're making your game, character has to move right when you hit the D key or the L key if you're using the Y keys. So it's very, very specific, but at the analysis level, you care about that you need an entity to represent the player. You need a calendar entity. Very high level, basically, but you're kind of structuring the problem here. Design then, so that was actually a great answer, was that you take and iterate what you get out of analysis. We move to design, where basically we take this object-oriented model that we've created and try to implement requirements from that. So you're going from a very high-level, coarse-grained model of your system, and we're a little bit finer-grained here. We're at the level where we can write out these requirements. And again, these are your measurable, quantifiable, both functional and non-functional requirements that you all have done already and are patiently awaiting feedback. And then we can also iterate that model a little bit further. Now, we are not programming here still. We are modeling, we are developing our software artifacts, we are basically still kind of structuring our project with zero implementation that's done so far. Right, so the second bullet point here, I've got implementing in bold, but this isn't program implementation, it's let's add new objects. Let's try and realize some of these high-level models that we created before, refine them to be a little bit closer to the problem that we're dealing with. Add maybe some calendar widgets to support the needs of everybody in this project, right? So we are refining things. And refinement, if that's a term that I haven't said enough yet, that's where you take something and you give it more and more and more detail. Conversely, refining can also mean going back and fixing things. So if you had a problem at this stage, again, high level diagrams, high level objects, maybe you don't need this particular entity, maybe it's misconstructed in some way, we can refine it and fix it here. So again, we are going in different levels of granularity. And I found this little, well, it's basically a screenshot of a slide online. It's kind of a good way to think about these things. And it basically uses the same terminology as I talked about when we briefly talked about verification and validation a while back. Analysis is going to be do the right thing. Design will be do the thing right. And that's a fun little play on words, but basically analysis, you want to be figuring out what the actual problem that you're trying to solve is. You are engineering a solution, well, you're engineering what the problem is. You're specifying exactly what is going to have to be solved, right? If you don't understand the problem you're solving, how can you construct software to handle it? Right, so let's take an example. Some of you are working on a magic mirror. I think that's actually in the other class, now that I think about it. But the problem that they want to solve is scheduling, news, all kinds of things in one place. That is the problem domain. We are developing objects to support that, but basically we're figuring out where the boundaries of this environment is. The design then implements that. and implements it by constructing artifacts and objects and requirements. So we are still kind of at the level here, again, where got a weird glitch over here, which is fun. Basically, the key takeaway here is not to really, beat a dead horse. We're still doing modeling and artifact development. We're not writing code at these levels. And this is something that I've really tried to hammer into you, hopefully by this point, that projects are never strictly about programming, right? It's super easy to jump in and just write code and write code. But then that works for little projects. It works for even term projects, things that you just throw away and you're done with. But if you have to maintain these things, if you have to work with other people, it's going to be very problematic if you don't spend the correct amount of time simply thinking about the problem, writing down what it is, and then trying to figure out, okay, what do I need to solve this problem? So that's analysis and design. If any of that sounds interesting to you, then you probably have a future in something like project management or software quality or assurance or something of that nature. Basically, if you care about understanding the problem domain, analysis and design is going to be right up your alley. So we take that, right? So we have our models we create during analysis. We refine them in our design phase. OOP then takes those models and realizes them in some programming language that is generally object-oriented, right? So you have pretty much all done OOP in the Intro to Java class. If you took Intro to Python, I mean, I don't know what the course content is there yet, but you probably talked about classes. You probably talked about, your basic programming constructs. OOP is there. I know one of you are doing a C program for the last homework assignment I put up, which is awesome to see. And you can coerce OOP concepts into a very procedural programming language, which is wonderful as well. But what do we care at this phase? Is it coding? It might not necessarily even be coding when we are structuring the project here. Yes, we have to write the code at this point, but we might still be considering things like applying design patterns. We might be considering how can we structure our classes, our packages, everything, relationship-wise, inheritance-wise, information hiding-wise. Basically, how are we going to structure this project so that we have a nice, ideal way to work together as a team? And again, maybe we do some more refinement here. Are there other objects we need to include? Are there other objects that we need to remove or update? Because, hey, this sounded great when we were all sitting around a conference table, chatting about how we want this to work. And then you sit down and try to write the code for it, and it's just functionally impossible. Maybe there's an API mismatch. Maybe there is just something that you can't do because you don't have the particular module. You can still refine your models at this point. You can still go back and fix things. But don't spend hours and hours and hours basically going through that analysis paralysis design pattern, which is a term that I absolutely despise to say because it's one of those business buzzword terms, but you can actually get into the bad habit of spending too much time in analysis, too much time in design, and then you never get to the programming, right? Because there's always something you can go back and fix. There's always something you can refine later on, right? But if you spend too much time doing that, then you never do your project. And if I had a nickel for every time I did that for a little hobby project, well, I'd be very rich, and you can see why I have no real good projects released and making millions of dollars out there. All right, so here is your standard object-oriented programming model of a system, right? You have some kind of an object, it's going to have methods, it's going to have attributes or variables or operations, right? Basically, you have a standard class. This should be nothing new for you here, but it's kind of important to get the idea of start with analysis, go to design, go to programming. This is all going to be within the object-oriented domain, more or less. Now, if you go to work for somebody like a car manufacturer, you go to work for GE or somebody like that, where you're working on little embedded systems, are you going to be doing object-oriented programming? It's iffy, but you can still take all the concepts that you learned here and try to apply them. So let's talk about some of the design principles that we have here. Now, this is where you can really take the power of the object-oriented paradigm and really try to make your projects a lot easier to structure, easier to work on. So we have some terms here, which I'm going to guess you probably have heard of in Intro to Java, but we're going to touch on them again just to make sure that we understand how they can be applied at a project level. So encapsulation, information hiding, reuse and interfaces, things of this nature. It should hopefully sound familiar, right? We talked about a lot of these in passing when we talked about design patterns, right? Like we talked how some of them rely on interfaces. Encapsulation was one of those things that you don't necessarily want to break because it's your design principle that breaks a lot of your patterns. Or information hiding, that's your public versus private versus protected. And you don't want to show everybody your operations or your class structures, right? So these are basically going to be the principles that we have to follow here. And what does this get us? It brings us to reuse. Reuse being some of those other types of relationships that we have, right? There's the generalization, composition, aggregation, all those fun terms we talked about before. But reuse is it's a very interesting term for us because this means that we can take components that we've developed over time, reuse them across our project, reuse them in other projects. And if it's structured well, that will save you time in the long run. So some of these design patterns that we talked about that promote reuse means that, hey, this view that I created for my MVC, Java application that the mean professor made me do, well, crap, I can reuse that in my term project. All I have to do is copy the code and maybe tweak its interface. So a lot of this idea of reuse is intended to really make projects function a lot in basically a lot more streamlined. So hopefully this is useful to you at least. So we have these principles here, and we'll talk about them. And we also have our interfaces. Now, interfaces are things that I haven't really talked about in detail yet. I'm hoping you talked about them in Intro to Java, but we're going to basically talk about them in terms of project design and analysis. And the key takeaway is that if you're going to be working on a project, generally you want to program to some interface, and I will go over why that's important, right? We don't want to program very, very specific implementations all over the place. You want to program to an interface and then have that relate to other things later on. So an example that we'll talk about in a little bit is a vehicle. Well, what is a vehicle? Vehicle can be anything that moves. So if I want that vehicle to move forward, do I care if that means spin up a boat motor, or does it mean, trigger a car engine? We don't care under the hood. We care about accessing the interface and telling it move forward. Might sound familiar if you remember that whole facade design pattern, right? All right, so let's start with encapsulation. We have some software engineering-y terms that were developed in the 70s, which still apply today. And encapsulation is one of them. This is where we bundle things together. When you create a Java class, you get encapsulation for free, right? You have your methods, you have your attributes, you have your privacy constraints. They're all baked into a normal Java class. Do you get that in Python or C# or any of your other languages? Absolutely, but some of them you have to go a little bit beyond to specify that. Like when you declare a Python class, everything's kind of free form and you have to really construct what is private, what's tied to the class, what's encapsulated, so on and so forth. C# is it's basically Microsoft Java, so you also get that for free. I guess let me know, is this all review for all of you at this point, or is this new for some of you? a refresher. Okay, that's good at least. The key takeaway is that even if this is horribly boring and something that you know, like off the top of your head, like encapsulation, data hiding, all that fun stuff, it's used differently at the analysis and design level because this features in with all of your design patterns. And I'm going to guess in your intro to Java classes, you didn't get all the design patterns, and they all rely on encapsulation or inheritance or data hiding, all that fun stuff. So you get your methods, you get your attributes, you basically get everything encapsulated. And let me show you my little picture here before we go back. This is not specific to object-oriented programming. You can apply this to any language where you can basically aggregate things together. In C, you can do it with structs and function pointers. Um, in Okay, so here I've got some other examples. So add a modula, um, the functional language ML. It's a meta, I think it's literally meta language. Basically, you have constructs which are out there for packaging things together. Again, bundle data, bundle operations, that's encapsulation. So you have a package construct in ADA, you have a module construct in modula. ML, you have ABS type. In C, you can basically do some pointer trickery. And again, pointers, if you don't know because you only ever took Java, that's a reference to a memory address. You don't care what's at that memory address. Could be data, could be function. Who knows? But I actually have a little link here if you want to create a map data type in C. But the key here is that we're bundling things together. That's encapsulation. Think of before, we're going to talk about cohesion and coupling more in a little bit. Cohesion's where we have a nice focus, right? When you encapsulate things together, that should be focused on whatever is encapsulated. Now, one of the key points here, and this is basically one of the things that are hard to really, not hard to realize, but maybe it's a misconception. Information hiding and encapsulation are always kind of talked about as the same thing. Wooden vacuum on a wooden floor is kind of what I'm hearing. Basically, data hiding, that's that private protected public notion. You get that with encapsulation, but encapsulation doesn't automatically mean that information is hidden. Right? If you make everything public inside of your class, it's still encapsulated, but it's still open for the world to see. So the question that I got down here, how could you have data that's not hidden but encapsulated? Make everything public. It's not hidden, but it's encapsulated, right? So kind of the key is that you bundle things together. You make some kind of an object and you bundle variables, bundle functions, relationships even together inside this class. Now, can you encapsulate multiple classes? Might be one question you would have, and the professor thinks you would have, but probably wouldn't because you're already, half of you are probably already checked out now. Sure, you could encapsulate multiple classes, right? We have that superclass, subclass relationship. We could have things kind of packaged together. Well, actually, that's a bad example because that breaks encapsulation. But if you have like a child class where everything is kind of nicely bundled and hidden away from the world, that could be encapsulated. So, a little bit about information hiding, because this is an interesting thing to note from a software engineering perspective. This was first brought up in 1972. So this is an relatively old concept for computing. Introduced by somebody named David Parnas, who is one of the leaders of software engineering, basically one of the pillars. So a lot of really neat work has come out of his research groups. But the key here, this notion of object-oriented information hiding came out in the 70s. Did we have Java in 1972? No. We had C, and we liked it. We had assembly, things of that nature. You know, some very early programming languages we had. We didn't have all the very fancy object-oriented languages you have today, but they all rely on this concept. And why do we care about information hiding? We don't want our client modules, right? So anybody accessing your class, they don't need to know what your data looks like. They don't need to know the makeup of your internal structure. Basically, you want to hide things that are in the quote here is that if it's a difficult decision, if it's a design decision, if it's important data, you should hide it from other modules, right? Because you want that class to only be working on this problem. You don't want somebody else's module to come in and start mucking about in this very important decision. So ideally, we structure things in such a way that it can't be accessed. And this leads to design patterns and things of that nature. So the key here at the bottom too, so I mentioned that encapsulation is not the same as information hiding. It facilitates information hiding. So we can hide our data, hide our structure within encapsulation, but we have to make sure that we specify everything is private or protected or something like that. So if this all makes sense, we have some rules for information hiding. These are hopefully common practice for you at this point in your lives, but you never know. It's possible that you still make everything public just to make life easy. The key rules here are to, first of all, make sure you don't expose your internal data. So all of your data items should be private. You should use operations to access them. So if you have data in a class, it should be private. If you want other people to interact with it, create a public get method. If they need to update it, create a public set method. Is it extra effort from your point as a programmer, right? Why can't I just call class dot variable and access it directly? You can, but this basically allows you to do something called defensive programming, which is a fun term to say. Basically, what this term means is that you are protecting yourself against future problems. Maybe something in the environment crops up that could break your program, right? Maybe something happens later on where a client tries to access your data and they set a variable to an incorrect state and that just breaks the whole program. Could be another programmer, could be yourself at 3 a.m. programming a new function, thinking this is the best thing ever. Then you run it and it just seg faults or crashes or whatever your favorite horrible program failure of choices. But if you have get and set operations, you can very cleanly show how to work with this data. You could even add in like guards where you can never set a value to be outside a range or outside a different enum or something like that. So the key is that try to use gets and sets where possible. And I know that Java at least automatically can create these for you as well, I believe. So it's generally a good idea. Extra typing, yes, but good for encapsulation, good for information hiding. Other thing to consider too, this might be new, I'm not sure for you, but don't tell other people, and I say other people, I mean other modules. They don't need to know if the data is directly set or if it's derived. And the difference between derived and stored data is that derived means that you have updated a value based on some internal logic, right? So I have derived speed from velocity and direction or something of that nature. Basically, I have made an internal calculation which results in some value. That value is derived. Other classes, other API calls don't need to know that. So get speed, for instance, in this example here, we don't care how speed is calculated. Could be stored directly, could be derived. The other classes don't need to know that. Last but not least, well, two last but not least here, don't tell others what the structure of your class is. So internal logic, internal operations, internal variables. Basically, other classes don't need to know that. And obviously, if they're associated in some way, if they need to access some data, provide some kind of a public method or some kind of an interface to talk to. But basically, hide your internal structure. Be very private. And then the last one here, don't expose implementation details. It kind of goes hand in hand with structure. But the key is, I almost kind of like to treat this mentally as protecting yourself against an attack or an unintentional misuse. Now, I'm Going to guess some of you have made websites before, because this is a very nice example of that. Don't expose your SQL statements. That's a good way to get people breaking into your database by doing like an SQL injection type of attack. Always validate your user data, always, all those kind of web design terminologies that you hopefully might know if you've never done web design, but be able to protect yourself. All these concepts apply to project design. And the key thing here is there's two problems to deal with that defensive programming helps to solve. One, either somebody's intentionally trying to break your program. Maybe they're trying to get details about your algorithm, how it works, or they're trying to inject their own data into their, that's one thing to consider. But oftentimes you're also going to have other people working with you or using your module who don't understand how it works, and then they use it poorly, and then that breaks everything, strictly because you didn't hide some of these things. Key takeaway though, encapsulation is not information hiding. That's up to you to actually handle. Okay, everything making sense so far. Kind of my key takeaway is defensive programming is a good thing, and encapsulation and data hiding leads toward that. And if it helps to visualize things, pretend like people are trying to hack your system, or that your users are absolutely awful people who don't even know how to turn a computer on, yet they have access to your API. But a little figure here to really hammer the difference home. This is encapsulation. If you look for encapsulation on Google Images, it's all pills for some reason. But variables functions are inside there. The data hiding is the private, public, protected aspect. All right, so on to some of the more deeper concepts. So reuse, again, that's where we can reuse modules, reuse functionalities throughout our projects. Typically, this is enabled through two terms. So we have inheritance and composition. Hopefully you remember that when we talked about our early UML diagrams where you have like superclasses and subclasses where the subclass inherits from the superclass, be like your generalization, for instance, or strict inheritance, I suppose. And then the composition is the other side of things where you have a bunch of parts, and when you compose them together, they make up a new big object, right? So it's like a system and a bunch of parts that go into that. These are two ways that we can handle reuse. Other terms for this, so if you use class-based inheritance, that's called white box reuse. If you use object-based composition, that is black box reuse. Have any of you heard of the white box versus black box functionalities? Maybe not specifically to this, but like in general. Do you kind of know what those terms mean? Because they're very, very common in CS and any kind of engineering, basically. Negative. Ooh, good. Pretty much any type of engineering problem will have some kind of a white box or a black box thing that you do. There's white box and black box testing. There's white box and black box program flow. There's white box and black box dynamic models. So basically this term is going to be used over and over and over again for you all. White box you can see inside. Black box you have no idea what's inside. So if I'm doing something in a black box format, I am sending data into it. Things happen inside this box that I cannot see into. Data comes out. I have no idea what's going on inside of it. White box, we have access to the internals. We know exactly what's happening. So that's the concept there, basically. You're going to see it time and time and time again, I can assure you that. But the notion here, basically, and how this factors in with reuse, basically when you're inheriting things, you know exactly what's inside these classes. So you have a superclass with a bunch of methods and attributes and all that, and then you have a bunch of subclasses which inherit from that parent class, right? So if the parent class is a vehicle and it's set speed, change direction, and you inherit, the subclasses will also have access to those methods and variables. So basically with this notion of white box, we know exactly what's happening. We're also strictly breaking encapsulation by doing this too, which is not always a good thing. But the nice thing here is that we have a lot of customization possibilities. So effectively, we have a bunch of subclasses we can customize. The downside is that you have to manage all of this. So you don't just have a nice little black box to plug numbers into or to take and reuse elsewhere. You have very specific class layouts and association rules to inherit, and you have to manage all that. But being customizable can be a good thing too. Again, trade-offs. It's going to come up every single class probably. 2 weeks after, there you go. That's a very fair statement. Everything becomes a black box after you're done. So the other side is the black box reuse. And again, this is where we don't know what's happening inside. Basically, take all these parts, compose them into a new class, basically, right? So you have your assembly or your system or whatever you want to think of it as. This is a black box where we don't know what's inside. Everything is encapsulated nicely. Data comes in, data goes out, and it has been changed. You can take this black box and stick it wherever you want. It's simple, it's clean, we know what has to go in and we know what's coming out. The downside is a lot of times this just isn't feasible, right? Are you going to make a package that can be reused in every single project that you've ever done? It's tricky because you typically need to customize things, right? So you're probably, if you're lucky, you can do this all the time. More than likely, you'll probably be doing something a little bit more open, a little bit more white box-ish. If we need a refresher on composition and inheritance, inheritance is your is a term, composition is your has a. So a house or a building is a house has a bathroom. So the bathroom here would basically, well, sorry, the composition would be a number of rooms would make up a house. A building is a type of house. So we have a kind of implicit knowledge of what's going on in here, but we could also consider this to be a black box made up of a bunch of different rooms. So is a versus has a. And it kind of gets into the structure of how it's implemented, right? If you look at this figure, you can say, well, I'm going to know everything that's happening inside anyway. True. But if you're inheriting, you have to know these classes. But if you're composing, you might be just getting this object as a reference. So let's talk about this in a little bit more detail now. So inheritance, this is again where we're like doing a superclass and a subclass kind of thing. Also, we'll call them our generalization class and our specialization class. And I realized I just missed a S on bolding there. But this is where you can inherit. You can do your superclass, and then you have another one that like extends other class, right? So you're bringing in its attributes, its methods, as long as they're public or protected, right? There are rules what the subclass can and cannot do, but it's something we can share, and then we can extend it. Now, the nice thing about doing this kind of a thing is that we can easily specialize. We have a generic superclass. Half of our work has already been taken care of. If we need special functionalities, added in a new subclass. So it's easily modifiable, which is nice. But again, you have to know everything about how it is all structured. So the one thing that I mentioned earlier, I said it wrong and then I mentioned it. Inheritance actually breaks encapsulation. So this is one of the downsides for a nice, elegantly designed program. So breaking encapsulation, what does that mean? We have gone beyond our class. Our single class is no longer contained within itself. We are exposing our implementation details to a subclass, right? Whoever is extending the superclass knows everything about the implementation. They may know internal details, internal data, internal logic, and that breaks our data hiding principles. So in theory, this could be a bad thing. Now, I'm kind of like nitpicking here in details, right? So we're breaking encapsulation. Okay, fine. Who cares? It depends on what you want to expose. If you want all of your implementation details well hidden, if you don't want any other classes to understand what's going on, this is something to avoid because you're doing that exposing here. So it could be a bad thing. It could be a good thing though too. Again, trade-offs. Since it's white box, since we are breaking encapsulation, we now have details that are visible. Right? Maybe we have protected methods where nobody else outside of this package knows what's going on, but our superclass and subclasses can all interact. This could be a good thing because that leads to customizability and flexibility. Yeah, it could be good, could be bad, just depends on your perspective. The downside, though, is that I've got it in red here and bold. If you change something in the superclass, you may have to change the subclass. So if I update get speed to be get speed and um, I don't know, speed and velocity and direction so that I get all my different um, movement metrics that I need for my various algorithms. Well, my subclasses that are calling get speed now have to all be updated, and all my subclasses that are looking at particular variables may need to be updated. Hopefully you're kind of getting the point here that customizability is good, but the downside is that you may have extra effort to change things around. When I talk about the black box reuse, my classes wouldn't care. They would just have one standard interface to the system here. So it's a little bit what do you prefer doing and what does your project need? Other aspect here is that we don't have anything that can be changed at runtime. So we talked before about like a visitor pattern. We're composing in different algorithms, different attributes, things of that nature. Anything that we are inheriting can't be changed at runtime. So basically, when we define an inheritance association, this is compiled. It's not something that you can easily change. So if you start mucking around with runtime adaptations, it's going to basically not work very well. All right. So then that was inheritance. Composition, get my little red dot off the screen. Here's where we are using that composition relationship, right? Basically what we're actually doing, is we're delegating. So if we have some particular behavior that needs to be done, let's delegate that to our composition object. And the nice thing here is that we can actually take advantage of some dynamically handled operations. Basically, think of that visitor pattern where things are coming in at runtime, where we are picking objects as the program executes. That's effectively what we're doing here in a way. Now again, we're going to provide a standard interface to that, but we have a lot more flexibility with what can happen at runtime versus compile time. So that's kind of the nice thing here, honestly, in a way, right? Before we have great customization capabilities, but it's static. Here we have very flexible use of objects at runtime, but they're not easily changeable. And honestly, this particular strategy is not always going to work because, again, you generally need functionality and customization. But the first point here is that anything that we're composing is going to be accessible through an interface. That's where I said at the very beginning, program to your interfaces. I think, yeah, interfaces are coming right up, so we'll finish with interfaces. But that notion of an interface is that you just have a generic entry point to this composition. Get speed, set speed, not all the internal logic of your engine or steering wheel controller and all of that fun stuff. You just care about this nice little interface. This gives you good encapsulation, good black box reuse, and in theory, everything is encapsulated and hidden. So you're accessing this black box. You don't know what's going on inside. Data is all hidden, methods are hidden, structure is hidden. You just talk to the interface. Downsides here, you may end up with more objects. You may end up with things that happen at runtime that you don't necessarily want to happen at runtime if you're picking like different algorithms or different objects like that. And you have to be very, very, very careful with your interface design. Now, we can use very simple methods that we're calling, but maybe you're passing in a reference to a class, or you're passing in an object that has to be operated upon. Your interface has to handle that. All right, so black box versus white box is the thing to take away from inheritance versus composition. Now let me show you a little snippet of an interface, and then we'll talk about it, and then we'll be done with class for the day. So I'm hoping that you all remember defining an interface in Java, but basically here we have a class diagram demonstrating an interface. So here we have two objects which could be moved around a screen. So you have basically a pixel or a circle. You could easily see how this could extend to a square, a rhombus, whatever primitive you want to draw to a screen. So what is the difference between these two here? Well, I've got my interface and I have some specific classes here. Now, we have actually an aggregation happening here, but we have some specifics. So the point has an x and a y, an x speed and a y speed. It's got a movable point function, so basically, are we changing it? We have a toString function to probably report out its location or something like that, called a move up, move down, move left, or move to right. That will interact with these attributes. Circle is going to have a radius and a center. It's not a point. It doesn't have an x and a y. It's got a reference to movable point, which is kind of nice, right? We can reuse things by having an interface and kind of aggregating here. But this doesn't necessarily need to be movable point. This could be x and y, could be x, y, z, could be a vector. I mean, who cares? It could be whatever we want. You could add another class on here, movable square. Well, I'm trying to think of a good example that doesn't use this particular class, since you would have probably the bottom left and top right corner, or top left and bottom right corners as points. How about array or something like that, where you have a x and a y and then a direction or something like that. But the key here is that your internal structure, other clients, other classes don't care about any of this, right? They just want to move the object. So they instantiate this movable class here and just call object.moveUp. Now, if that's simply a point, well, the point moves up. If it's a circle, the point moves up, and then you also had to have your radius for drawing the point. If you had a square, it would have to move two movable points. That is internal to your movable square object. And if my kind of hand-wavy movable point square idea doesn't make sense, you'd have a reference to your top left and your bottom right point, and that would define your rectangle. That's all the info you need for that, really. So if I wanted to move that up, I'd have to move each of these points up. That would be contained within this class. And again, it would be hidden behind this interface. Hopefully that makes sense. I didn't try to talk in circles there. Looks like we're actually pretty much out of time, so we'll pick back up here next time. But the key takeaway, program to an interface, not an implementation. Make your internal logic hidden behind an interface is kind of the key takeaway. Then you have good data hiding, good encapsulation. Any questions at all from you? A lot of talking from me, not a lot of talking from you all. So hopefully that all made sense. Other than that, I will see you all on Friday. We'll wrap this up and we will do some more analysis and design. It will be fun on the bun. All right, good? Well then, I will see you all later. Have a wonderful, slightly chilly Wednesday, and yeah. See you Friday.